So today we have Dr. Kevin Tang, who is from Yale. He is a postdoc associate at Yale, and his main areas of interest are experimental phonology and phonetics, and computational phonology and phonetics, and computational linguistics and corpus linguistics, and it's like about every area of linguistics he has something to say about it. Yeah, and actually Dr. Tang even has a degree in engineering. Before he got his PhD in linguistics, he got a degree in engineering, so we have a very highly competent individual coming to this lecture, so I really like it. And you can ask him questions during the lectures because he's nice and tells us that we can interrupt him.
Please
if something is unclear. Yes, if anything is unclear, please raise your hand and ask away. Okay? And you will have time at the end of the lecture. Okay? I think you can. He will ask me in 5 minutes.
Well, thank you for having me here today. It's a real pleasure to be talking to both faculty members and MA students. So I'll be essentially telling you a range of studies that I've been conducting over the years. And I've been finding that essentially speakers and listeners, obviously they have prior lexical and phonetic experience. They live through their adulthood, they learn the language. But more specifically, they seem to be able to form expectations about certain aspects of their respective languages. And they will use this expectation to condition fine details of speech production and speech perception. So one of the kind of ongoing issues or challenges, if you like, in phonetics and phonology is variation. It's very tricky. We're dealing with it every day. So if we take two different languages, doesn't matter which two, and you will see that they share similar sets of phonemes, particular common sounds, and yet these phonemes might be produced or perceived rather differently by individual language groups. This could be anything from subsegmental properties like voice onset time, or closure durations of stops, or formant values, if you like. Doesn't matter what. Kind of subsegmental structures of the respective segments. So when it comes to variation, we have to look at the kind of classic work by Cho and Ladefoged. So this is a very classic plot, and essentially it's showing the mean voice onset time values of velar stops across 18 different languages. So you have on the left very small things like with very small voice onset time called Angami, and all the way to the right you have Navajo. And the researcher thought, well, let's sort it by low to high and group them in some ways, and they found like 4 clusters of some sort by value alone. But they don't cluster in any meaningful way, they don't cluster by typology. So what's going on? Moving on to some sets of my own data. So this is a language called Cypriot Greek, and they have a very interesting kind of long and short consonant like Italian, and they're phonemic. So I have long T and short P, long T, short T. And if you were to take the duration of the long consonant divided by the duration of shorter consonant, what you would get is like some kind of ratio, and it should be always above 1, because long divided short. And here we're plotting essentially those values for each kind of pairs, long P divided short P, long T, short T, etc. It's grouped by some kind of manner of articulation. So what do we see here is like some variation, but they don't seem to vary in any systematic way. Why would the velar kind of stop be less contrastive, you like have a smaller duration differences than the bilabial and alveolar? Why that one? Why not the other one? Why is the sh more contrastive in ratio than s? What about look at 2 different languages, Cypriot Greek and Italian? So we just saw earlier on Cypriot had lots of internal variation. What about across languages? Both Cypriot Greek and Italian, both of them have long and short consonants. And here we see that, yes, the contrast between the bilabial and alveolar stops are bigger than the velar one. But in Italian, the contrast is less kind of obvious. It's more fairly marginal. In any case, the direction is different as well. So why do we see 2 different languages sharing the same set of phonemes behave rather differently? Moving away from production to perception now, this is a very nice study I like by Harnsberger. And essentially, you're seeing 2 kind of plots here. And you can think of it as it's called multidimensional scaling plots. The distance between the sounds, the labels, indicate how perceptually distinct they are. The closer they're to each other, the more confusable they are with each other. So here, focusing on the top kind of left, we have the perceptual space of nasal stop by Marathi listeners. On the right, we have the perceptual space by Punjabi listeners. And the crucial point is some of these segments are phonemes in both languages, namely the palatal stop and the alveolar stops on the top left. Marathi listeners have no trouble perceiving them. They're different. I know one is dental, one is nya, they're different. Punjabi listeners, though, although it is both of them are phonemes in this language, but they find it very hard to perceive that they're actually that different. So to recapitulate, why do we see 4 groups of VOT values across 18 languages? No obvious typological grouping. Why do we see internal variation within Cypriot Greek in terms of this long divided by short ratios? And yet why do we see differences across languages between Cypriot Greek and Italian? And moving in the perception side, again, 2 different languages, Punjabi and Marathi, having same set of phonemes, but they are warped and shaped in different ways. An answer some people would give is, well, it's language specific. Languages are different, and that's the way it is, and we can go home and have a cup of tea. But I don't think that's good enough. Labeling something is not simply explaining it. Giving you an example of kind of explanation you can give to this kind of language-specific pattern, I'd always like to look at the Oman study in 1966, classic. So basically it was investigated the articulatory kind of pattern in vowel-to-vowel coarticulation. If you get a vowel, consonant and a vowel, how much coarticulation do you get between the 2 vowels with the consonant in the middle? In English, it was found to have a stronger vowel-to-vowel coarticulation of backness, meaning how back the movement of the tongue, if you like. Whereas with Russian, the vowel-to-vowel coarticulation is a lot weaker. Essentially, there isn't that much coarticulation. Then we see the language-specific pattern here, right? English, very strong vowel-to-vowel coarticulation. Russian doesn't exist. Why? Well, an obvious explanation is because Russian has contrastive consonant by backness. You have palatalized consonants and plain consonants. And English doesn't have that, so it allows for more flexibility. It's not phonologically encoded, it's not important. So this is one kind of example of a language-specific explanation you can give. So more generally, we should ask ourselves when we see a variation, is it a random variation? Is this purely accidental, from historical accidents? Or maybe it's principled, right? Maybe you can predict it using general kind of language general principles of communication and make fine-grained predictions about exactly which segment is going to be different from this segment, from this another contrast by how many milliseconds or by how strong a degree. The next question we want to ask, okay, is what are the actual factors that are shaping this kind of general principles? And the next question is how? How are these factors shaping fine details? So the what, well, whether it is random or not, and if it's not random, what are the language-specific patterns, and how are they actually influencing perception and production? And I'll be presenting to you with some evidence that a lot of this variation, I reckon, is owing to the fact that speakers and listeners have statistical expectations about their respective languages. We know our languages, obviously, and they would have expectation over segments or words. And I'll be showing you specifically that speech production, perception, and the lexicon, they interact in a specific way. And this specific way is driven by a certain communicative principles that are language general. There's more handout at the front for those who arrive a bit later. So I'll be drawing evidence from a range of languages, not just English, which is that is kind of boring, to be honest, and to try and replicate several important lexical effects that's been shown to have an effect on speech perception and speech production. This effect obviously has been reported again and again for very well-resourced and well-studied languages like Spanish, essentially most of your classic Indo-European major languages. And methodologically then, I would like to extend this to see whether I can model aspects of production and perception on under-resourced and understudied languages with small and noisy datasets that are collected outside the ideal laboratory settings. So no sound booth, no fancy equipment measuring every detail. You go to the field, capture data. Can we use this small noisy data set to make concrete predictions that essentially match those that are better studied in better resource languages? So to highlight the point home, can we basically see that small and noisy data sets needn't be bad data set? So for the benefit for a lot of the MA students here, I know you have the computational branch and theoretical branch, I hopefully provide you with examples of the kind of work that you could do yourself with what you've been learning in your course. And essentially, I try to put theoretical work, experimental work, and computational work in action. So the roadmap of today's talk, first off, I will have two studies, both of them on segmental level variation, one on production and one on perception. And this one, I'll be specifically be focusing on kind of a graded notion of phonological contrastiveness, because I'm a phonologist. And moving on the word level, I will see whether this kind of top-down effect can be extended on production of Kaqchikel words and on the confusion or perception of English words. I'll talk about that later. So the first study, which is basically going to be focusing on the Cypriot and Italian examples I provided much earlier. And this is collaboration I do with Professor John Harris at University College London. And I'll be showing you that speakers and listeners have knowledge of this graded notion of phonological contrastiveness. And they will use this to do phonetic enhancement for contrast preservation. So first off, then you say, oh, Kevin, come on. You know, I did Phonology 101, you can't fool me. Phonology is always categorical, isn't it? I mean, we have complementary distributions, either yes or no. Don't have anything gradient. Well, some people would argue otherwise, right? More recent models have been highlighting there are a lot of graded effects of contrastiveness in phonology. And two dimensions I'd like to focus on today. One is called functional load, and one is called distributional overlap. Focusing on the first dimension, functional load, what is it? Well, you can think of it as the amount of lexical work two phonemes has to do. Or the other way of thinking about it is the number of minimal pairs two phonemes share. So take English, for example, the p and k, you can find minimal pairs, right? Like pat and cat, pit and kit, and so on. And, but you can imagine certain pairs of segments, you'll have a much harder time finding minimal pairs, like her and egma in English. Actually, I don't think you can ever find minimal pairs because one is always at the onset, one is always at the coda position. So there's the degrees of minimal pairs two segments share, or the amount of lexical work that they do. So a more general hypothesis here is that sound pairs that are phonologically more contrastive in this graded notion will be more hyper-articulated than those that are less contrastive. So people have shown this effect already. I'm not the first one to jump into this kind of camp. But they've been working on mostly English or Spanish, and they, for example, they find like the degrees of acoustic contrast in tense and lax vowel in English, the E and E contrast, is stronger for those pairs that are phonologically more important. And same thing with VOT values in voice, kind of voices stops like per, ter, ker. And today I'd like to, for change, work on Cypriot Greek and Italian and see whether we can replicate this kind of effect on kind of different languages, right? So a more specific hypothesis here is that the size of the durational difference between the long consonant and the short consonant in these geminate singleton languages is reflecting the amount of lexical work that they do. And so first of all, we need to focus on the acoustic dimension, the durational difference. As I already mentioned, the classic way of modeling this is this ratio. Why did they do it? It's because duration is a universal attribute for this contrast, because it's about long and short consonants, so you pick on duration. And if you were to do this for your bunch of languages in the kind of a meta-study, to survey all these German singleton languages and look at the values of this long divided by short, you'll find a lot of internal variation, as I've already pointed out in the Cypriot Greek example, everywhere, right, the values were. But if you look at like kind of average ratio for each language, you also get like a huge variation. Something from 1.5, which is like meaning the long consonant on average for this language is 50% longer than a short consonant, to something like 3, I think that's Japanese actually. So this is like a long consonant is 3 times as long as a short one. Why do we see such a variation, right? Why are they not consistently double? I love them if they were double. Fits the phonology better, but it doesn't, unfortunately. And so I argue that this kind of variation is owned by 2 factors. First off, is the kind of durational cues that we take into account when computing the ratio. There are different durational cues, not just one, and I'll be telling you more about that. The second one being the amount of phonological contrast a specific language decided to use German and singleton for. So language A might use this contrast for, let's say, to form 2,000 minimal pairs, all of them high-frequency ones. Language B might say, oh, I have this contrast too, but I'm only going to use it for 200 minimal pairs, and they are kind of low-frequency words. So it's less important for language B than language A. So in terms of the choice of the durational cues, the most important one is definitely closer duration. If you measure it phonetically, it's always found across languages that have this contrast. And second kind of very important cue is called the preceding vowel duration. So that's the duration of the vowel before the consonant. So you have like, let's say, so Italian are like that. So fatto, right? So the duration of the vowel before the long consonant could actually also indicate this contrast, not just the consonant itself, which is the closer duration. All the study when they computing these values, they use closer duration, and some of them also measure preceding vowel duration, but I argue that you should always measure it and take that into account, providing the phonology tells you to do so, namely for reason of quantity and isochrony. So Italian as a good example. Italian usually described as a quantity-determined stress system kind of language. Very roughly speaking, you can say that all heavy syllables, meaning a syllable that heavy with vowels and consonant or long vowels, the whole rhyme is occupied, are heavy. All stress syllables are heavy, and all heavy syllables are stressed. So there is a quantity kind of determined stress system. And the durational cue, the durational information encoding the long and short consonants, is actually distributed over 2 syllables. So take the word fate, fatto, which is long vowel followed by a short consonant, or fatto, fact, short vowel followed by a long consonant. So the locus of the durational contrast is not just the consonant or just the vowel, but rather is VC, both vowel and consonant. The orthography might tell you that, I think they spelled the long one double with double T and the short one with 1 T. This orthography will tell you it's the consonant that's encoded in the contrast, but the phonetic tells you otherwise. Okay, so given the phonology of the language independently telling you that Italian, you should really take into account the preceding vowel duration. You should be computing the duration of both preceding vowel plus close duration. And in fact, the phonetic supports that as well. If you were to measure people saying long measure saying fatto, fatto kind of thing, you will find there's a compensatory effect. Long consonant would have a shorter vowel in front, and the short consonant will have a longer vowel in front of it, slightly compensated. But you do not find this effect for Cypriot Greek. So for Cypriot Greek, we also know that independently it's not quantity-determined stress system. So for Cypriot Greek, you're only using closer vowel, closer duration, but for Italian, we're using both durational cues. So this is really saying that we need to look at the phonology before we take into account of how we're measuring the ratio. Okay, so now we know how to measure the phonetic side. What about measuring the lexical side? So we need to compute functional load. One simple way, just count how many middle pairs, like pat, cat, kit, pit. Or you can take into account of token frequency. So a more fancy way of doing it, but I don't think it's that much more advanced in terms of the variance explained in the data. You can think of a language that consists of a set of units. Units could be syllables or words. People focus on words most of the time. And now you pretend that, okay, so it's a sequence of words, so you're encoding some information. Now you present some of the words that have long P and short P are now one and the same thing. So long P and short P are now no longer 2 different phonemes. They are now one and the same. So now the language is slightly compressed, right? They've lost information now. You lost some words. So you compute the proportion of information lost. And that's how you compute the functional load of long P and short P, by pretending that they don't exist and recompute the information contained in the language. Okay, the first study on the Cypriot Greek, we're using like a kind of meta-study approach. We take the values from Avanitis data, paper, and across manners and place articulation. The lexicon is a bit more dodgy. It's not a ginormous 500 million word of Cypriot Greek because people don't really write that language. We're using a very, very dusty old dictionary. I think the University of Cyprus dug it out and they typed it all up and they basically sat down and read every single word and crossed out the one that they don't know. And that's the corpus. Really, really, I would say, rudimentary, no token frequency information. In any case, we push on, we do what we have, and let's run some analysis. So on the x-axis, we're showing the functional load of each kind of long divided by short pairs, and the y-axis, we're showing the durational contrast, right? The durational difference, the ratio. So we're seeing some kind of correlation. R squared is pretty good, 30% for such a crappy data set. And the L contrast, long L divided by short L, has the highest functional load, and on average it also has the highest durational difference. And the SIR, all the way up to the corner, has the smallest functional load, so you don't find many minimal pairs, and also has the smallest durational difference in the production of in the phonetic space. But we also see some weird thing going on with the outlier there. The rate is completely off the chart. So what's going on there? Well, on the whole, we see that, okay, there's a correlation. Functional load seems to be a good predictor for this durational difference. And we also see this outlier, and it's a good thing, it's a healthy thing to see it, because independently, it's always been reported, you can't use that value, because the long one is always a trill, the short one is always a tap. So you have different manner of articulation. A tap is something like vere, or like on Spanish, how is it? Can't think of any word. Para, that's a tap, or para, that's a trill. So you can't compare them. One is a trill, one is a tap. You can't compare all apples with oranges. So that one is consistently outlier, and we found it to be outlier in our functional load kind of examination as well. Okay, moving on to the phonetics data of Italian now. So we're taking Esposito study, focusing on the stop series, pataka badaga. And the lexical, now we're using something more fancy, like a 100 million word corpus, transcribe it phonemically, compute functional load values. What do we get? We get a pretty healthy correlation this time, 90% variance explained. And on the right, you have the ter, so this is factor kind of minimal pairs. It has lots of little minimal pairs of that type, and obviously it also has a very, very big durational contrast. For the G, long G divided by short G, you have a much smaller durational contrast, and it is also the one that has the fewest minimal pairs. So it's really good that it seems to be capturing the variation in the phonetic space using a lexical dimension. You might ask, well, Kevin, you said you have to look at the phonology, right? You have to look at phonology, determine the domain of the cues and all that. I don't really believe you. I just want to use close duration. That was a universal attribute of this phonetic, this German singleton contrast. Just use that. Well, I tried everything. So I tried exactly that, computed it over the closer duration alone, and computed over the preceding vowel duration. Essentially, you get no correlation, non-significant. But when you put 2 and 2 together, magic happens. You get really strong correlation, highly significant. That really shows you that you can't just run random correlation. You need to know about the language before you conduct any kind of analysis of this type. Otherwise, you get these spurious correlation issues. It's very common in linguistics nowadays. And so to sum up on this study then, functional seems to be a strong predictor of this singleton durational contrast, and speakers are sensitive to this graded notion of phonological contrastiveness, namely functional load. And they will use this knowledge to enhance the acoustic space to basically preserve certain contrast. So imagine this. For contrast preservation, meaning I want to be able to preserve things so that you can recover as a listener. If I want to do that, I can just enhance everything, right? I hyper-articulate everything. Fa, do, and I know fa, ro. I can hyper-articulate everything, but I don't do that because I'm cheap. I'm economical. I only hyper-articulate the things that need hyper-articulating. And we also highlighted the important look at the phonology, before we decide on the phonetic domain that the cues are encoding in. And this kind of top-down effect, I argue, is pretty robust because the data is pretty grand. The phonetics data of this type, believe it or not, what they do is that they grab a male speaker, a female speaker, usually 2 of them, give them 3 minimal pairs, 4 minimal pairs, get them repeat each one 3 times, and that's it. You don't get 500 participants reading 6,000 minimal pairs, nothing like that. Very few participants, very few items, and yet you seem to be able to capture this fine variation. It seems that this effect is really robust within each speaker. And also the lexical data as well, we don't get a ginormous 500 million word. A crappy dictionary pruned out by native speakers is perfectly sufficient. Okay, so that's the first part, telling you basically that we as speakers use top-down information to modulate fine details of production of segments. And now I'd like to show you the same thing for the perception of segments. So this is work I collaborate with Professor Brian Bennett at Yale University. And I'll be showing you this, that listeners have statistical expectation of lexical information and acoustic information this time. And both of these factors, acoustic plus lexical, are affecting speech perception in a very fine-grained way. And I will argue again it's a robust and strong effect because we will be examining the time course of the effect in perception. And we'll find this effect pops up almost immediately So it's a very automatic mechanism as opposed to like a post-hoc decision-making mechanism. And also the task that we'll be using doesn't tap into any lexical knowledge. The task itself doesn't require the participant to access words. They can do it without it. And yet we're seeing lexical pattern affecting the speech perceptual processing. So the language of interest is called Kaqchikel, which is a Kaqchikel branch of Mayan language spoken in Guatemala. And I think last year, I stalked the website, 2 of your students took the course, MA course, and went to Guatemala to learn this language. So for those people, this would be particularly interesting. For those who are not those people.
They're not here because they're second year.
Okay. Next year, go to Guatemala. Yeah. And this, like, yeah, something to look forward to, you see. This language is pretty cool, I have to say. Because it has this stop contrast of plain and glottalized stop series, which is really cool. So it has something like this. Per, which is a normal per. Also the implosive ver, so per, ver. And the other glottalized stop is ter, k, and I can't do the last one very well. I think it's like k, a bit kind of creaky. And this kind of contrast has basically rarely studied in the perceptual space for across languages and never studied for Mayan, so it's always good to do something novel. And we'll be quantifying and examining the perceptual confusability of these stops, of these consonants. And how do we do it? Well, we try to keep the task very simple. I mean, the participants are basically, most of them are farmers, and they don't use computers. They've never been tested. They're not your average psychology students off the street. They're very, very sort of normal people working on the countryside. No, never used a computer before, I think, half of them. And so we need to keep that very, very simple when doing this kind of field experiment. And the task is this. You play them essentially 2 sound files, usually syllables, CV, consonant plus vowel, or VC, vowel plus consonant. The vowels are always identical because we don't care about those for the moment, but the consonant could sometimes be different. So to give you an example, hopefully this works, I'll to play a specific trial that we use in the experiment. Well, it's noisy, right? So I'll repeat it. It's supposed to be noisy, by the way. Right, so it's saying something like ak, and ak, with noise added, because without noise it's so simple. You want to keep the task a bit difficult, so you added noise on it to make it harder, to generate errors. And so participants will have to press same or different. If they got it correct, they'll press different, because they're different. But if they mistakenly press same, that will be an indication that these 2 stops are rather similar. If they consistently make mistakes for these specific sound pairs, again and again and again and again, then maybe these 2 sounds, k and k, are quite confusable and perceptually rather similar. So this is what it looks like in the field. So we don't have a fancy sound booth in the village of random village of Guatemala. It's a classroom that we borrowed from some very nice people, and no soundproof wall whatsoever. No, even we just used 2 random table prop together, a laptop, button box, and a headphone, and that's it. Chicken could be running on the outside, by the way, while this was happening. I think we didn't do it during that time. Yep. So that's really showing that you could bring the lab to the field, right? You don't always need to work on languages that you can randomly grab participants off the street. You can go to them. Okay, so I talked about examining acoustic effects and lexical effects on speech perception. So we need to be able to quantify them first off, right? How do you examine them if you can quantify them? So to quantify lexical effect, we need a lexicon or corpus of some sort, which doesn't exist for Kaqchikel because these people don't read nor write their own language. So we built our own very strenuously. Essentially, we took any digitized text that we can find. Doesn't matter what it is. Religious text, spoken translate, governmental document, textbooks. And we use web mining techniques and OCR, a bunch of books as well. And the result of that is 1 million words, which isn't that big, right? If you take any corpus these days, it's 500 million. But compared to the classic English corpus by Kaqchikel and Francis, I don't know whether you know of it, it's called the Brown corpus. It's still being used in psychology for some crazy reason. I don't know why people still use it. It's very, very, very bad. And yeah, so it's actually the same kind of size. In any case, we should always criticize our data set. I can't just trust it, like, oh yeah, I built it, I'm going to estimate stuff from it and believe it. No, how can I believe that it's actually real? Maybe it's so bad that any lexical measures are just purely useless. So I need to criticize my own data. So first off, I know it's not big, so statistically speaking, low frequency words will be poorly estimated. It's not speech-like, right? I mean, governmental text and religious documents, not your average Kaqchikel farmer's reading list. And really noisy, OCR errors, typos, and so on. For this reason, we apply a range of filters to really try to clean things out. And we'll also evaluate it in multiple different ways, which I'm going to do right now. The first thing I like to do is evaluate its representativeness. Please.
So what does it mean, OCR?
OCR is an optical character recognition. So you know sometimes when you scan a document, and let's say you scan a book in a library that you didn't want to pay for it or something, and you want to be able to search for the text, but it's kind of a picture.
Oh, yeah, okay, I got it.
And now you can still kind of search it. That's OCR. And which is not always very good. It makes errors all the time, so it would confuse certain letters like, I don't know, O with C, or so that's why you get some kind of error. Sorry about that. What was I saying? Yes. So first evaluation is going to be the representativeness. So I want to see what the corpus consists of, right? So I could look at the percentage of documents that are religious texts, the percentage of documents that are governmental documents, but I don't do that because that's boring, and I want to instead visualize it. I like to do data visualization. So what I did was this. I computed the frequency of every two words, the background probability, and plug it in as a Markov chain. So it works like this. Imagine I computed the probability of I am in the corpus. Let's say that's 66%. And I did the same thing for any other pairs of words. So here, the probability of I followed by am is 66%, and probability of am followed by Sam or Kevin are both 50%. Imagine you keep on growing this kind of tree. So it's a kind of long Markov chain. And now you can use this to generate random text, which is pretty cool. And you might have seen this kind of technique. People use this all the time. I think there's a new thing about like generating recipes recently on Twitter. And you can essentially now let the chain babble random Kaqchikel texts, and that will let you see the kind of content in the corpus in general. So this is a sample of the text. We evaluated different versions of it. I can't read this, so I translated it, Ryan translated it into English, and we look at some of the key words, right? Like something about wormwoods, something about it hurts when he urinates or has sexual relationships, and Democratic Republic of Congo, Jehovah. So hopefully you will see that its vocabulary is quite broad, and which is a good thing. You want a broad vocab when it comes to computing lexical measures sometimes. And it's also pretty quick as a technique when you quickly visualize how representative your corpus is, what kind of language is it. But it's hardly your average Kaqchikel farmer speech. They don't talk about government stuff issues, they don't care about Congo. I don't think they even know Congo where it is. And they definitely don't talk about Jehovah. So it's not very speech-like, but viral vocab, so it's pretty good in some ways. The second evaluation I'd like to do is on the kind of prediction the corpus can make about independent facts of the language, especially by the lexical measure they extract from it. So here I like to focus on, again, functional load, because we'll be using this in the perception study, and probability of sound mergers. So it's a decade-old hypothesis that if two segments have very, very few minimal pairs, imagine, let's say, he and, or as an example, per and ter, let's say they have very few minimal pairs, but it doesn't, then over time, the probability of these two sound merging as one is higher. And I can't think of, I can give you a candid example, but that doesn't help. Yeah, so it's been shown to be, there's a correlation or relationship. So if two sounds are not used a lot over the in the lexicon, over time they will disappear, which kind of makes sense. So in Kaqchikel, then there's a very interesting diachronic kind of cross-dialectal merger between the tense vowel and the lax vowel. So the system works like this. They have a 10-vowel system, I, E, or U, classic. It also has the kind of more centralized lax vowel. I can't do the lax one, but you can imagine they're kind of lax. And so in the language that conserve like all 10 vowels, it looks like this. But if a given dialect decided to lose one of the lax vowels, it's going to lose the A one first. And the next dialect, let's say, oh, I want to lose another set of lax vowels for some reason. It was going to lose both A, O, and U. And the next one going to be lost is E. So it's this kind of hierarchical order of merging pattern going on. So the question is whether we can predict this pattern using our functional load measure, whether I can predict that the A1 should disappear before the O and U, and before the O, and after the O and U it should be E. Can I predict that? Well, kind of. Pretty well, I think. The lowest functional load vowel pairs is the A1. The next one being O and U, and the next one being I and E, and they're both pretty high actually. So on average, I've actually repeated this for other measures, and essentially can make pretty good predictions about diachronic or synchronic cross-dialectal variation. So yes, it can make independent predictions. Third, sorry.
How many dialects were included into the mergers hierarchy?
Oh, I think there's like over 15 different Kaqchikel dialects or something like that.
With reduction.
Oh, it's the one that actually
reduced systems.
Yeah, okay. I will tell you that most of them have reduced system. The only one that we preserve all 10 is Solala. The rest, all of them, most of them look something like this. Some of them looks like this. I can't give you the exact number. But I would say that this only exists for one language, one dialect, Solala. Yeah. And I think there is one that have, I think in the perception study that we're going to do, the participants are from Patricia, and they have this version. And interestingly, this pattern doesn't seem to cluster in any geographic way. we try to see whether geography can explain that pattern, but it doesn't seem to be an obvious one. They talk to each other all the time, and so you expect lots of contact issues as well. Does that answer your question?
Yes.
Okay, the third evaluation is on the size of the corpus. So when you're doing kind of corpus building for minority languages, every token costs money, right? Imagine you go to the field and do recording and transcription. Every token costs money. Written corpus as well, it costs like time to process it and clean it up and tag it and morphologicize it. So we want to know how big corpus needs to be in order to do the kind of work that we do. Because you kind of will get a diminishing return after you reach a certain point. You don't need a billion, I truly believe this. The difference between 1 billion and 2 billion is nothing. You don't need a 500 billion word corpus when maybe 500,000 words is sufficient, depending on the dimension of the property that you're extracting. So in any case, we want to evaluate then how stable our lexical measures are going to be. If we see like how stable are they going to be across different sizes of the corpus? So if we see that the lexical measures are going to fluctuate like crazy when your corpus is pretty small, let's say 5,000 tokens or 10,000 tokens or 0.1 million, and it doesn't really stabilize as you grow the corpus, then perhaps you can't trust the corpus in terms of lexical measure. But if you see that on the lexical measures, they stabilize really quickly, then it means that you can stop collecting data after a certain point, because after that you're wasting effort. So we didn't do that. What we did is we sampled from our full corpus. We grab 1,000 tokens and grab another 1,000 tokens and keep on adding it. For each size, we are going to recompute the functional load value. We recompute that 100 times, or 100 different samples for each size. So lots of simulation going on. And we're going to get this plot then. So on the x-axis, we have a different sample size, all the way from 0 to a kind of 1 million. On the y-axis, we have the functional load value for the 5 10-slash vowel contrasts. So the bottom line is the A and U, O, and R and E. So we see that, okay, in the beginning it's kind of crazy, right? We kind of cluster together, but it kind of diverged really quickly. It diverged basically after 10,000, well, it got stabilized and flattened out around 10,000 words or so. So around this point. So you don't really need a 1 million word corpus to get this stable estimate for this specific set of contrasts.
Sorry, could you explain about this graph? So
right.
the axis is the size of the corpus, right?
Yes.
And the y?
It's a functional load value for the tens-lax contrast.
I'm asking because I don't understand why it is monotonous increase, because at the beginning we would expect real jumps, and why shouldn't it start?
Okay. So you expect it to kind of go really crazy at the beginning?
Right, and then to stabilize over time. Yeah.
Yeah, I can tell you why a little bit. I think it's because actually I repeated this not over words. I repeated this also over syllables. Because this kind of contrast is so robust, you don't even need words. Syllable itself is enough. So that's why even in the very, very beginning, you already see a difference. The very, very small sample, you can already immediately see a difference. For this, because if we're talking about tense lax, contra, or vowels, vowels are very, very common in language. And the syllable shapes are, okay, syllable shapes is a different story. But maybe it helps if I give you a different contrast, that consonants. Consonants are more complex. So something like this, more noisy, maybe that's what you want to see. So this is the plain and glottalized stops. So they do it again, that kind of contrast. I computed over, let's say, 7 pairs here. And in the beginning, it goes pretty crazy, and it also gets overlap quite a bit, even around kind of 10,000 words or so, and it only really stabilized around sort of 2 to 30,000 words. So yeah, so for certain contrasts, you do need more data, and yep. But still, you don't really need a ginormous corpus. That's really the point I'm trying to highlight. Does that help?
Yeah, I think so, because I just at first I didn't really understand this rich behavior of the birds. Now I see that.
Well, and the reason you get this kind of fuzzy line is that's computed because each sample size we did it over 100 samples.
Right. So it's yeah, I got it.
And yeah, okay. So this kind of evaluation that we did helped us to see that our small and rather noisy corpora, or corpus, beg your pardon, using very kind of pretty bad data sets, like religious text, government documents, are actually okay. In terms of how representative it is, I mean, it's not speech-like, but has a broad vocabulary size. You can, using the Markov chain babbling, it can make prediction about the language. And it seems to be that the lexical measures are pretty stable over time, over size. So our corpus seems to be big enough for doing the kind of lexical measures that we want to compute. Obviously, if you're doing something syntactic, you see a way bigger corpus than this. So yeah, so we can be reasonably confident that the kind of measure that we're using can be trusted, and now we can actually use them to predict speech perception of our participants. So these are going to be the lexical measures that we can be extracting, and in speech perception, there are tons of lexical measures, and we always present this, and people say, have you considered this one as well? So we added a lot of them, we evaluated all of them. So wordhood, word frequency, segmental frequency, neighborhood density, neighborhood frequency, but more importantly is the last two. These two are more novel. Only recently people tapped into these two great notions of phonological contrastiveness, functional load, and distributional overlap. So distributional overlap, I haven't explained this. And essentially is this. Imagine her and sir in English. They have moderate amounts of overlap in terms of the environment they're occurring. By environment, I mean adjacent segments. So let's say adjacent segment being the segment on the left and on the right of a given segment. But for her and Egma, one is always an onset, one is always a coda. So actually you would not expect them to overlap very much because they occur in different environments. They're fixed to a certain constituency. So this is a degree of overlap in the environment that we're interested in. Okay, so we have explained the lexical corpus. We have evaluated it in different ways. We have computed a bunch of lexical factors that we can use later. Move on to acoustic side. Acoustic corpus, we're using basically a pretty small corpus again, consisting of 16 native speakers, giving us like a short narrative of their own choosing. Essentially, we sat them down to tell us a story, and they give you all sorts of stories. And we process around an hour worth of it, orthographically transcribed it, phonemically transcribed it, phonetically transcribed it, and enriched it with force alignment, which is a kind of hidden Markov model for those that are interested. And the output of the force alignment, which is pretty cool, can be visualized like this. And this is a specific word, a given audio signal. What you do is you tell the force alignment tool that this signal contains this set of segments. Sh, s, ch. And the force alignment tool will try its best to capture a certain portion of the acoustic signal to that segment. Yeah, that's clear. So this bit is the R, this bit is the ch, and so on. You can see the alignment isn't perfect, but it's good enough. Okay, again, we should self-criticize. And the spontaneous speech it is spontaneous speech, so it's pretty natural. But it comes with its own set of baggage. Essentially, spontaneous data tends to be have data sparsity issues because that's natural. So, example, the ejective I mentioned earlier on is actually a very, very, very rare segment. Across this corpus, it occurs 18 times. And similarly, in our written corpus, it also occurred very, very rarely. Which can be an issue, right? Because if you only have 18 tokens, how good are your estimates? If I want to estimate acoustic property of the 18 tokens is not good enough. And also, it's spontaneous speech, but it's narrative, not dialogues, right? Every day you don't talk to a wall about telling them, you're not a storyteller, you talk to people, you communicate. So in that sense, it's not very natural. And we have evaluated this jointly with the written corpus in a next study. So you have my word that this acoustic corpus is not a crazy corpus, it does reflect some psychological reality for now. Okay, so in terms of the acoustic parameters that we're going to estimate, based on the very simple hypothesis, greater acoustic similarity predicts greater perceptual similarity. If two sounds are similar in the acoustic space, they're going to be similar when you hear it in the perceptual space. Pretty obvious, right? And there are essentially two kinds of acoustic similarity that we want to measure. The first kind being stimulus similarity, which is the similarity of the acoustic recording in the experiment, the here, ak, and ak. How similar are these two recording themselves? And the second kind of similarity, which I really like, is called category similarity. You can think of that as a similarity of two phonemic categories based on my Kaqchikel listeners' prior phonetic experience. It's always good to do some visualization, so let's look at this cartoony plot. Imagine I am a Kaqchikel native listener, and I'm, let's say, 20-odd, I'm 30 years old now, and I have lots of statistics. I have lots of experience about Kaqchikel. I store fine phonetic memory traces of my own language, and I can use them, I can extract them. So I have all my voice onset time of ke, the phoneme ke, and they're distributed in such a way on the left. I have the same set of values, but for per. Crucially, they do not overlap. The distribution of BOT values of ke do not overlap with the distributions of the BOT value of a per. And the blue dots is a specific instance of ke on the left, and the specific instance of per on the right. And you can think of that as what the experiment actually presented. They presented it with a specific kind of instance of ke, ka, and a specific instance of pa, pa. So they hear ka, pa, ka, pa. So for me as a listener, a participant, I can do this specific trial very easily. Oh, I know that the ke is always a ke, the per is always a per. Different. But in the alternative universe, things are not always that nicely cleaned up. The two self-distribution could overlap quite a bit in different degrees. And now, I'm doing the same task again, the same trial again. Oh, I don't know, is that a ke, is that a per? I know that they overlap a lot, sometimes in my prior phonetic experience, so I'm not really sure. So for that reason, I might accidentally press same as opposed to different. So now, how do we actually quantify both of these similarity, right? Like stimulus similarity and category similarity. We're using a technique called dynamic time warping. There are other techniques too, but we're using this specific one in this study. And you can think of it as a signal processing technique plus Levenshtein distance, for those who know what that is. So essentially it's like in Levenshtein distance, you're kind of trying to align segments, right? It could be letters or phonemes. But in dynamic time warping, the units can be warped in the temporal dimension. So you look at the plot on the left here. You have two waveforms, the top one and the bottom one. The lines are not straight. Instead, they're kind of warped in the kind of x dimension. Okay? The one on the right is kind of your classic Levenshtein, if you like. It's kind of a straight line. Okay, so for the stimulus similarity, we computed over the two acoustic files for each trial. For the category similarity, we extracted all the kers and all the pers in the acoustic corpus and cross-compared them. And the result of that is now we have our lexical corpus independently validated, and we extracted a bunch of lexical measures. We have our acoustic corpus also validated independently, extracted some of the acoustic measures like category overlap, and now we're ready to plug this into our model to see whether these factors, lexical and acoustic, can predict fine details of speech perception by Kaqchikel listeners using their response accuracy. So how accurate are they in pressing same versus different? Using a mixed effect logistic regression model. So after lots of kind of model pruning and nested model comparison and so on, we arrive at our best models. These are the explanatory factors. So what is playing a role here? Okay, so the acoustic factors are obviously playing a role because it's an acoustic study, it hears sounds, so it makes sense. The first one being similarity. Yay, obvious one, right? If two sound files are similar, they will of course make more errors. But perhaps more interesting is the second one, category similarity. That is, the similarity of two phonemic categories overlapping in their kind of prior phonetic experience. And the more overlap there is, the more errors they would make. And this is really crucial because this effect is above and beyond the similarity. We put both of them in a model. What that means is that listeners in the past, they're not just doing kind of low-level auditory processing using their kind of cochlea and so on. They also tap into phonology. They tap into the language. They're using their own individual language-specific experience to modulate their speech perceptual processing. So phonology and language matters, apparently. And there are also lexical factors, too. So functional loads, already pointed it out already. So the direction is this. If two segments have lots of binary pairs, they will make less errors. They will be more accurate in differentiating them in the experiment. In distributional overlap, if two segments have a lot of environment in common, they will make more errors. And we also find a weak token frequency effect, which is again surprising because we're talking about words like CV and BC, and actually only 10% of them are words. So given how few stimuli are words, actual words, we still find a token frequency effect is kind of surprising for this kind of task. So, okay, we have the warp now. We know that this factor plays a role in warping the perceptual space. Granted. Next question is how? What is the actual mechanism? So we want to ask specifically about the kind of lexical factors. Are the lexical factors an automatic mechanism affecting the perceptual processing directly? Or is it like a post-hoc decision making? So it could be that I listen to some items, some phonetic memory signals in this, some phonetic signals in the trials, activate a bunch of words, a bunch of syllables, and I computed functional load, distributional overlap. And after I computed it, I used it to aid my task. I could be doing an online computation. So which one is it, online computation or automatic mechanism? Well, let's look at the response time. Look at the responses that are quick responses, mid-range responses, and slow responses. Divide them by 3 bins. So in the quick responses, Python answers within kind of 400 milliseconds, which is pretty quick. And we see all the factors we pointed out earlier to be robust immediately within 400 milliseconds, and they slowly decay over time. So this is really pointing towards the automatic account, as opposed to a post-hoc decision-making account. So yeah, so in this study, I've highlighted this kind of exemplar style, this kind of cloud style of phonological representation of phonemic categories, or even words, right? So we don't just have knowledge of k and p, we actually represent it by fine-grained memory traces based on our prior experience. And these experiences are shaping speech perception. And second of all, we highlighted this great notion of phonological contrastiveness again. And this is again warping the perceptual space. And these are both of these effects are robust and automatic because they occur in early time course. And again, the task is an age discrimination task. They have to press, are these two sounds same or different? It doesn't ask you to find words or anything. So why on earth would they still tap into the lexical knowledge, right? So it really shows that it's a kind of low-level tuning of the perceptual system as opposed to a post-hoc calculation of functional load and distribution overlap. Okay, so to conclude the first 2 studies, we seem to see that on the kind of fine-grained phonemic level, speakers and listeners are biased by their kind of statistical expectations of words as well as, of segments and especially subsegmental properties when they are doing speech perception and speech production. So I'd like to really attribute this kind of top-down effect in terms of acoustic enhancement, which I've already mentioned, and perceptual tuning. So it seems that speakers are only enhancing the cues that are important. By important, I mean important for encoding phonological contrast. And they're also paying more attention to cues that are important in terms of phonological contrast. And jointly, these 2 mechanisms, acoustic enhancement and perceptual tuning, are maximizing the recoverability of the information in the signal, while minimizing the resource cost. If I just, focus on the first point, recoverability of the information. If I want to maximize that, I can just enhance everything, right? I can just make sure everything is extra hyper-articulated. And I can also pay attention to every single acoustic dimension and all the cues. Right? If I do that, I'm maximizing information in terms of recoverability. But again, I have mentioned already, we're cheap, we're economical. We don't like to do that. We want to save money or save cognitive cost. And under this kind of view then, a lot of the language-specific patterns that I pointed out earlier, in the Cypriot Greek example, within the language or across languages, in the Marathi and Punjabi listeners example, all these language-specific patterns can in fact be predicted or explained by language general principles that are grounded in communication. And I want to attribute this kind of communication to like a Shannon kind of information theory sense. So you can think of communication as communication through a noisy channel. Like talking to you right now is pretty noisy, right? Because the room is echoing and I might be speaking a bit fast and you might be tired in the evening. And so this channel can be quite noisy. And communication is optimal under this channel sense if the information is transmitted uniformly through the channel. Imagine a channel like a pipe, right? If I transmit too much information too quickly, pumping information through the pipe is going to burst, it can exceed the channel capacity, I'm actually losing information. Or I might understand information, I might turn a little bit, and have lots of space left in the tube. But now I'm wasting resources, right, when I can actually put more data through. So optimal transmission is to pack it uniformly throughout the channel. Okay, so going back to the kind of effect we've been highlighting, functional and distributional overlap, this graded notion of phonological contrastingness. In a way, they are basically predictability. And they are predictability over different lexical dimensions, right? And so the next natural question to ask is, does predictability have a more general effect over different linguistic structures, namely words? We found that predictability matters when it comes to subsegmental properties. Does it matter for words? So then move on to the next two studies, showing the word duration in Kaqchikel and word confusion in perception of English. So first off, the Kaqchikel study. I'll be showing you that there is an inverse relationship between word duration and the predictability of a word in its context. By context, I mean adjacent words. So imagine the sentence, I'm going to the swimming pool. The word swimming is franked by the and pool. So the and pool are the context of swimming. Okay? And so we'll be seeing that the more predictable the word is in its context, the shorter that word will be in terms of production. Here we say within a shorter time frame. And this reflects this information theoretical account that I mentioned earlier. Essentially, it's a kind of acoustic enhancement effect. And there is a trade-off, right, between language redundancy, meaning how predictable a word is, how redundant it is, and signal redundancy, how much information I want to encode in the signal, namely word duration. So predictability comes in all sorts, lexical, syntactic, you name it. But closer to home as a phonologist / phonetician, we see effects in English, for example, TT deletion, a classic effect. People drop T and Ds at the end of a word, but they drop it in a systematic way, or cluster reduction as well. They don't just reduce any old clusters, they reduce them when they are predictable ones. And we also found at the phonetic level more recently that the segment itself, duration of a segment, or how the amount of reduction a segment is for consonant and vowel, are again predictable by predictability. So you will reduce the things that are predictable for segments, but now we want to see whether this effect occurs in words. So this is essentially kind of enhancing a study from Wright, showing that in the lab, if you sit people down, get them to read a bunch of words, and essentially for high frequency words, the predictable one, they'll read them in a shorter time frame, shorter word duration. Lower frequency words, longer word duration. And we want to see whether this kind of pattern, this inverse relationship, can be found in spontaneous speech, in kind of like a spoken corpus. And this has been done already, of course, on English, and we'd like to see whether it can be done on a morphologically rather different language, where word is kind of different now, right? For morphologically complex language like Kaqchikel, or which is essentially like agglutinative language like Turkish or something, where a word is essentially basically a ginormous sentence. And whether this kind of words can also be used in terms of capturing this inverse relationship. So we're using the acoustic corpus again, extracted the word duration of 10,000 words, And we computed a bunch of lexical measures using our not very good lexicon, word frequency, and bigram probability. So here is the probability of the word swimming given the word the, given the previous word. And the probability of swimming given the following word, pool. And also phonetic probability, like, which is the probability of a word given the subsegmental structure. Now we're using this predictability effect plus kind of control predictors to try to predict word duration. What do we get? Basically, most of them are highly significant. In what direction, though? In this direction, inversely. So here we're seeing the predictability of a word given the previous word on the x-axis on the top plot, and the predictability of a word given the following word, again on the x-axis. So as you can see that as x increases, as the word becoming more predictable, the word duration also decreases. So the more predictable the word is, the more probable a word is, the shorter its duration. Okay, so I've shown that there is indeed an inverse relationship between word duration and predictability. And the acoustic enhancement effect that I've shown you in the Cypriot Greek and Italian case study can be kind of extended, if you like, from segment to word level. And speakers actually have knowledge of contextual predictability, and that's a crucial point. Because they're not just storing information about word token frequency, they're storing the information, kind of rich information, right? They're storing bigram probability, essentially. They know that swimming always comes followed by pool, very likely followed by pool, and very likely followed by the, maybe. And they're using this information to enhance the signal accordingly. And this effect is above and beyond English. And so look at one of the Kaqchikel word here. Means they drove me crazy. I think it's pronounced shikishuk, yirisach. And you can see how many morphemes there is. And we're treating that as a word. And yet we're still seeing this inverse relationship. So this might say something about the communicative strategy when it comes to morphological complex languages. Maybe speakers are less sensitive to morphology. Maybe morphology doesn't play that strong a role when it comes to this kind of efficient communication methodologies. Okay, so finally, moving on to the fourth study. We want to see whether, when we're perceiving words, whether we tap into this knowledge of acoustic enhancement. And this is collaboration with Professor Andrew Nevins, and mostly based on my own PhD work at University College London. So I'll be showing you that listeners have expectations of the communicative strategies of efficient acoustic enhancement during speech perception. And when they're retrieving words, they will harness this relation, this inverse relationship between word duration and predictability, even when the process goes wrong, even when they grab the wrong word. So what do I mean by that? Well, this is essentially a case of lexical misretrieval. Imagine I say to you the word pit, but you misheard me as bit. So you try to grab pit, but you didn't grab it right because it was quite noisy, and you grabbed the word bit instead. So that's a lexical misretrieval. So this kind of word confusion patterns is the one we're examining, and we're using 3 data sets, 2 of which are naturalistic in the sense that these data are collected in the wild. These are individual reported data. So I have a bunch of students or people just report over the internet saying, oh yeah, yesterday I misheard my mum saying this as that. I misheard she or he saying pit as bit. These kind of individual reported data sets. Really noisy, right? I mean, who knows, they might misreport things. We don't even know half the time whether it was a genuine case of misperception. In any case, we push on. This could be misperception of conversational speech, like now. Well, not really like now, but and also of sung speech. So when you're hearing songs, but you misinterpret the lyrics, misheard song lyrics, okay? And the third case study is going to be experimental data set of single word processing. You play participant a word, add some noise on top of it, and you see, we get participants to type down or repeat what word they thought they heard. And we'll be examining the relationship, the predictability relationship between the intended word, like pit, and the perceived word or misperceived word, like bit. And to give you an example, it's always good to show you a picture of Woody Allen or a video. And so this is a case of conversational misperception by Woody Allen. And let's try to play this.
What skill don't you have that you wish you did? What fear? What skill? Oh, what skill?
Right. So he misheard, what skill don't you have that you wish you did, as what fear don't you have that you wish you did. So he misheard skill as fear. I mean, it's not completely crazy misperception, right? I mean, some of the segments and phonetic properties are similar. S and th both fricative, and r and l are both kind of liquids. They have a phonetic relationship, and the vowel as well, fear and sk, both kind of high front vowel. So phonetics is certainly playing a role here, obviously. So it's this kind of naturally occurring misperception that we're talking about. And that amounts to essentially 5,000 instances reported by individual over the last 40 or 60 years, I think. And in my own work, I basically compiled them and added more data points. And you can find it in this website, seerproject.org. And you can also report more data of not just English, of Russian, or any languages of your own choosing. And to give you and you can report it using a form or Twitter. You can tweet it, which is always nice. And the kind of data we have is something like this. You can kind of filter and explore it, and you have pretty rich demographic information for most of the data points. You know the gender, the age, where they're from, what accent they belong to. Yeah. So second data set, the misheard sung lyrics, which is also called Mondegreen. So this is a case of Will Young. Pay close attention to what he's saying. Singing, not singing. Let's try again, maybe. So well, I did this many times with my students, and usually it's a 50-50 split. Okay, let's see whether this is right. So a lot of people misheard leave right now as deep fry now, or deep fry it now. I mean, it's not completely crazy, right? I mean, fry it, right, leave, deep. I mean, there's phonetic relationship there, no doubt. And yeah, so some of you might misheard something quite different from this. I sometimes get some very weird ones as well. In any case, it's that kind of data set we're talking about. Reported misheard sung lyrics instances by individuals, and it amounts to around 20,000 cases. And the third data point, data set, is a single word misperception by individuals. So you set people down in the lab, you grab a bunch of words, individual words, you put noise on it, shh, or something, like apple, shh, and they try, oh yeah, maybe it's apple, they type apple, but sometimes they might type able or something different. So it's the erroneous instances I'm interested in. That amounts to 30,000 cases. And all three cases are pretty noisy in many ways, so we need to clean them. So we go into function words, proper names, and non-words, and so on. And we still get a pretty healthy size around 2,000, 10,000, 13,000 for each of the respective corpora. And we go to our analysis now. Very straightforward one. Is there a correlation between the frequency of the perceived word and the frequency of the intended word? And thus, do this kind of correlation, if any, hold across control factors like monosyllabicity, whether the two words are both monosyllabic or whether the two words are polysyllabics? And there are good reasons to do this, but I don't want to explain the Simpson paradox right now. And the second factor being the amount of segmental difference. So that is, imagine this. For the sound pair skill and fear, every single segment is different, right? There's no identical segments for skill and fear. But if you compare pit and bit, 66% of the segments are similar. So we're essentially seeing whether we will see consistent correlation no matter how many segments were misperceived. Okay, so complicated plot here. On the x-axis, we're showing the intended words frequency, y-axis the perceived word frequency. Red line is monosyllabic word pairs, blue line polysyllabic word pairs. You see these three bins? So the first bin is like 10% of segmental differences. The other bin is 40%, 80%. I also have other bins, but I can't show them all in the same plot. So what you see essentially is that the correlation is pretty robust, sometimes 30% to 8% of R square, and it's consistent across monosyllabicity and the degrees of segmental differences. What about the misheard sung lyrics data? Pretty noisy, but it's still, the correlation is still there. R square has dropped, but it's consistent across bins and across monosyllabicity. But the crucial one is the experimental one. In the experimental one, we get something pretty crazy here. First of all, some of the line goes negative, and half of them are flat. I mean, look at the red and blue line, 80% bin, and the red line, the 40. Flat line, basically no correlation, and everything is kind of squarey, right? It's like a square plot. So, and the R square is ridiculous. It's 0.005. That's, I can't even compute how many percent. That's 0.05% of variance explained. So no correlation, or no consistent correlation. Yeah, so I've already said that. Okay, so second analysis now is a common sense analysis. You might say, well, Kevin, surely when I'm uncertain about something I've heard, what I would just do is I just pick high frequency words, right? If I just pick high frequency words, I will have a good chance of getting it right. High frequency word occurs very frequently, so statistically speaking, I will get it right some of the time. So whether participants or listeners would do this, whether they would employ this kind of clever guessing. To do this, we examine whether the perceived word is consistently more frequent than the intended word. But this is a plot for the conversational data. So on the x-axis, we have the degrees of segmental differences. On the left plot is monosyllabic word, the one on the right is polysyllabic words. We're doing a t-test, essentially. The red line is like the degree of statistical significance. Anything outside the red line is significant. So we see that it's not significant across bins, across monosyllabicity, meaning that in the conversational data set, the perceived word is similarly, the frequency of the perceived word is similar to the frequency of the intended word. It's neither higher or lower. What about for the experimental data set? Something drastically different here. We see that in the experimental data set, perceived word is consistently more frequent than the intended word. So it means that people are doing this clever guessing, essentially. So why do we see this difference? Why do we see a correlation and, in the conversational data set, and that the token frequency is neither higher or lower? Why are they similar? Why come in the experimental data set, we see no correlation. Remember, the box is pretty squarish, and the perceived word is consistently more frequent. Why do we see different data patterns here? Well, I'll attribute it to the fact that perhaps on account that the perceptual system is really using any available cues, a keyword here, available cues, in the degraded signal to activate possible lexical candidates. And this is what makes the two data sets different. The naturalistic data set is rich in available cues. It's in a sentence, for crying out loud, and is spoken in a naturalistic setting, have pragmatic syntactics, semantic cues, and specifically also have relative word duration as a cue. Consider this, if I have a sentence, I'm going to a swimming pool, let's say you couldn't hear one of the words, let's say you couldn't hear swimming, doesn't really matter which word. You don't get any signal at all, but you still know how long it is, right? You still know how long swimming is relative to the other words in the sentence, given the speech rate and everything. But in the experimental data, you get no such thing. You get the words are presented in isolation. So you get no relative word duration. And furthermore, you get no word duration because in these experiments, for some reason, they like to control for word duration. They always like to pad everything so that every single stimuli is same in duration with noise pattern on each end. So with no word duration information, then what that means is that the listener will have to rely on their lexicon. So to explain that further, consider this. As a listener, I want to grab the most likely word because that's communication. I try to guess, give a best guess. I try to communicate. And if available to the listener, listeners would harness their knowledge of the efficient communication strategy. They will harness the fact there is an inverse relationship between word duration and predictability. So given that they have relative word duration available in the kind of conversational data settings, because they know how long the word roughly lasts, they simply have to grab a same approximate word that has the same approximate duration, and by chance alone, because of this inverse, not by chance alone, by this correlation alone, they will be grabbing a word of same approximate predictability. But in the experimental data, they do not have that cue. They do not have relative word duration. So they will have to fall back on the only thing that they have, the lexicon. In which case they do clever guessing, high, 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 as opposed to tracking details in the signal. Okay, so to sum up now, I have highlighted that speakers and listeners utilize their prior lexical and acoustic experiences when it comes to doing tasks like speech production and speech perception on both words and segments. So going back to the kind of initial starting point about language-specific patterns, a lot of them might seem random at first. Remember the plot with the Cypriot Greek, every bars are completely crazy. They might seem random, but I would argue a lot of this seemingly random pattern are predictable by this language general principle of communication. You want to communicate in a maximum efficient way, maximizing recoverability, but minimizing cost. And a lot of the randomness in the variation that we observe can actually be boiled down to how arbitrary the prior phonetic or lexical experience is. Many people in linguistics would mostly agree that the lexicon in itself is pretty arbitrary in many ways. But the reason why I pointed out that it's not actually that arbitrary. So first of all, we know, well, not that reason for this one, we know that the lexicon has a Cypriot distribution, meaning that there are very, very few high-frequency words like I, me, you, or in Russian, ya, de, the, and very many low-frequency words like accordion or extemporaneous. So this is the non-arbitrary kind of pattern. And word length effect as well. We're talking about not word duration, word length, how many segments a word contains. You will also find that high-frequency words are always shorter than low-frequency words. You can find this consistently across languages. Clumpiness of the lexicon. How are the words distributed in the lexical space? So you can imagine on the one hand, every word are kind of equally spaced out. A word is here, a word is here, a word is next, kind of everything equidistant from each other. But they don't do that. They cluster together in a way that I'll explain later. And finally, sound mergers. We have talked about this already. Low functional, low sound pairs would merge more likely over time. So this is again a non-arbitrary fact about the lexicon and how the lexicon would evolve. And I'm arguing that a lot of this non-arbitrariness are all driven by communicative principles. So first of all, Zipf-in distribution is driven by the principle of least effort. Why use every word equal amount of time when you can use a few very often and the rest not very often? Word length effect. So this requires a bit of explanation. So we pointed out this efficient communication strategy of words, right? This inverse relationship. Imagine a word across context, on average, is pretty predictable. So on average, this word would be quite short, right? In terms of word duration, it will be compressed in the acoustic space. If so, it could be kind of phonologized over time. Over time, certain segments are simply not heard because it's always compressed, and therefore phonologized into a citation form so that certain segments are disappearing and this word over time will reduce in length. Clumpiness of the lexicon. It's been pointed out in terms of perception on, I think, like Peter Graff's work across 40 languages, that he found that the lexicon is actually dispersed, or the space are clustered, in a way where every word is maximally distinct in the perception. So words cluster in a way that would minimize confusability. So again, it's non-arbitrary fact. Fourthly, sound mergers. So I pointed out the two mechanisms, right? Acoustic enhancement and perceptual tuning. Both of them are driven by functional load, as I already said. So you can think of it like this. If two segments don't have that many middle pairs, so I won't acoustically enhance it. Why bother, right? It's not going to be useful anyway. Again, these two segments don't have a lot of middle pairs. Why should I bother paying attention to it as a listener? If I don't say it very clearly, if I don't perceive them very carefully, they will disappear over time, naturally. And so I've replicated several, I would think, pretty important results showing that experience-based factor from the lexicon and the acoustic space influence fine detail in speech perception and production. And the important extension of that is I have shown this in languages that are different from English, in under-resourced, understudied languages, and that especially have very different kind of sociolinguistic and structural difference, right? So sociolinguistically, Kaqchikel participants don't, as I already mentioned, they don't do experiments, they don't even read or write their language, and compared to your average psychology student who speaks English. And the structural differences as well, morphologically highly complex, highly agglutinative. And we did all this using small and noisy data sets collected outside the lab. So the written and spoken Kaqchikel data sets collected in the field or over the web, pretty noisy. And the misperception data set as well, collected by individuals, highly noisy. I mean, like, who knows what they're reporting. And also the metadata set that we extracted from prior experiment, the Cypriot Greek and Italian studies. I mean, they're using 2 participants with few word pair 3 times. Very, very small amount of data. And yet all these small noisy data sets are making valuable contribution to psycholinguistic research. They do make sense, provided you clean them and evaluate them carefully. because, well, I like to use them because they are ecologically pretty valid, right? It doesn't get real than real data sets. And they're pretty complementary of what we know from experimental and theoretical research. So as a final point, I think as experimental/computational linguists, we need to equip ourselves with a range of skill sets in order to do the kind of work that have been demonstrated here. So we need to be able to construct, process, validate both written and spoken corpora. So we need to be able to extract VOT value, we need to be able to do force alignment, we need to be able to do data mining online, we need to be able to calculate bygram frequency and so on. We also need to have knowledge of linguistic theories, right? We can't just blindly explore the data. You need to know about the language before you can explore it. And in order to ask theoretically driven questions, which is very important. And thirdly, sometimes you actually want to step outside the corpora. You directly ask participants or probe them, get into behavior experiment. It could be questionnaire, judgment data, age discrimination tasks in the field, doesn't matter. If the behavioral data can further validate your results using corpora. So together then, we can probe the human mind by connecting facts that we extract or derive from corpora with psychological reality. And I think that is a really good thing that we should do as linguists these days. Okay, I think I will stop there.
Okay. Questions? Okay. If I could start with, I don't know. Okay, you have, okay, go ahead.
Students first.
Students first.
Well, so we measure the predictability of a lexical item, right? And when we do this, we should get rid of all the functional words, right? So this is here. I think this is an interesting issue because on the one hand we have this, for example, article the. And then we have a huge range of possibilities. So this would mean that we will have longer duration of the word after it, or we consider like the whole context. In the whole context, then we get rid of the function.
Okay, which study are you talking about here? The word duration study, or in general?
Well, this is more like in general, but if you have some.
Okay, so let's think about this.
You can refer to the particular study.
So you're saying that, okay, I said that sometimes I want to exclude function words, and first of all, why do we do it? I guess, is that one of the questions? And the second one is what the implication that would be to the results.
Okay.
No, I don't, wait, please clarify, maybe I didn't get your question completely.
So, yeah, actually this is, I guess this is the question, because what I mean here is that if we get rid of the functional word, then we measure predictability dependent on the context itself. Okay. Or if we don't get rid and we kind of only look at the preceding word, which is sometimes an article, then
not
we'll
an
get
article.
different.
Yes, I get what you mean. Yes. Very interesting point. So in the okay. So what we would do is this. They would filter out function words only in terms of the target word.
Exactly.
If the target word is the, and so I'm going to the swimming pool, so the preceding is to and the following is swimming, they would not consider the as a target word. But they would consider swimming, although swimming have contexts that are function words. So that's what the general practice is. And there's a reason why that's the case, because as been shown by work by Joravsky and a lot of work by Professor Ann Cutler, psycholinguistic researchers and computational researchers, that function words are processed pretty differently to content words. And in the sense of, function words, first of all, are more restricted in terms of the distribution, and they're quite predictable in some way because they're integrated with syntax, right? And so that's one point. And also, function words always are the ones that are highly frequent. So I mentioned that short words are more frequent. So sometimes people say, well, maybe if you get rid of, so let's say, people always say this, you find any kind of frequency effect, the predictability effect, people say, aha, it's because you have function words, right? That's driving the frequency effects. Why don't you get rid of them and see what happens? So that's the reason for behind it, for doing this filtering out. Because they are processed differently, supposedly stored differently depending on the theory that you subscribe to. And people always like to be extra conservative with their results by getting rid of things that could potentially contribute to the effect. So if you still see an effect after getting rid of function words, then your result is more robust. That is not saying that you should not consider it. Some people would actually build in an extra predictor of seeing like your extra binary predictor in the model, saying is it a function word or is it a content word. So I know that Jurafsky himself does that. And kind of an interesting point to this is it's not always clear what is a function word.
Yeah, sure.
It's really not clear at all. And this work has recently been done a lot by Florian Jäger. He asked me this question right before this book. Have you considered building a function word? I said, how do you build a function word in an accusative language? The function word is within the word itself, depending on how you define the word. And there's no, and even for English, right? How do you determine something is a function word? I really don't know. You can think of some category and some lexical item actually sometimes can be a function word, sometimes cannot be a function word. So I know that people sometimes use like people sometimes just do a arbitrary cutoff of high frequency words as a rough estimate. And for our study, I think for morphological complex language, I think we have to pay extra attention to it. Really an independent way of identifying it. Does that answer your question? A little bit more?
But I got one more.
So please.
So that's actually very interesting how we would deal with the languages that have, I don't know the exact term, but something like prosody harmony.
Prosody harmony.
I don't know if
Vowel
this term
harmony?
is probably. So with vowel harmony, which reflects in prosody, in this sort of thing. So for example, in Chukchi, we have vowel harmony, but actually we can say that depending on the structure of the word, some of other words that are like in the surroundings, they may become shorter or longer or something like that.
Okay.
So this is actually interesting because in this case, we won't be able to rely on the duration, right?
Let's see. So you're saying in this language, the vowel harmony process is dependent on the prosodic pattern of the phrase. I don't really know the language that you're talking about. But
I guess it's vice versa. First
Yeah.
we have the vowel harmony, and then sometimes it reflects, it kind of broadens its context.
okay. Yeah. What's the specific question here?
So in this case, we can't use these languages in this experiment with duration, right?
No, I think you can. You have to take into account of that fact that there are independent processes that are modulating duration. So you have to factor that into the analysis.
Oh, sure.
So a lot of the analysis, they put in lots of control factors to try, because people always you should always be extra conservative with your model. You see a result, you might be happy, but try to beat yourself down basically. Plug in things that you think explain the variance away until you couldn't plug in anymore.
Mm-hmm.
So in that specific case, I think you should plug in the fact that duration is modulated by the independent process and see whether word duration still plays a significant, predictability still plays a significant role in modulating word duration.
Yeah, I had a couple of questions.
Please.
About this yes, retrieval. I was wondering, you talked basically about acoustic factors of frequency, but I was wondering for your naturalistic data sets if you shouldn't be taking into account contextual factors, because if we're talking about something, it's like different from the experimental setting when you don't have any thoughts beforehand, but when you are talking, you have some things in your mind, so it seems that a lot depends on the individuality of the speakers or on what they're talking about, the topic of the conversation, so many outside factors that maybe I just didn't see how you accounted for them in your
It's certainly tricky, okay. So some of these factors beyond what we can account for. We can't account for pragmatic factors, it's very tricky. I mean, it could do it if it's actually possible. Some of the data set people actually report the context of conversation. So I could build a model that activates certain lexical item more strongly if it is in the topic of conversation. And semantic differences, semantic fact as well, could also play a role in syntactic fact. So I have examined this not quite like this. So I've also tried to included a semantic similarity between the words. So I use kind of fancy distributional semantics methods, basically called current statistics of words in a ginormous corpus, and see whether correlation still holds across semantic similarities. And it still does.
It does.
It does.
Okay. And I had another question.
And yeah, please.
Another question was this. So, am I right in understanding, like, let's say that we have a language, let's say, well, okay, let's speak about Russian, we have voiced and voiceless consonants, and some pairs of voiced and voiceless would be more frequent in, like, with this functional load, like, let's say, the t would probably form more pairs than the f.
Oh, yeah.
So does it mean that we would distinguish between d and t better than between v and f, and would make less mistakes and
yes.
so on? So it's really like just like that, yeah. So
well,
it will be easier for us to distinguish.
All else being equal.
So
obviously you have to capture the phonetic relate, like so. That's the Kaqchikel experiment. So remember, I also factor in the actual stimuli similarity, and on top of that I added in other variables. So after capturing the phonetic information about the seconds, and then we put in top-down lexical effects.
So you put it on top of the acoustic.
Yes, you have to, because acoustic obviously play a huge role.
Exactly.
So this is after acoustic, where the lexical things were still modulated.
Okay. And then I have one more, the last question. So then for language acquisition, for language learners, then it would be very different, obviously. But it would seem that with their competence in language growing, they would approach the kind of the patterns of the native speakers. So in the beginning, everything would be very difficult for them to distinguish. If, for example, like when I'm teaching like English speakers Russian, it's very difficult to teach them the difference between soft and hard consonants. I've never tried to actually measure whether it's more difficult to capture the difference between n and ñ, or r and re, and so on. So I don't know, really. But would it mean that when they become more and more competent, it would be easier for them to distinguish between the more frequent pairs and between the more rare ones?
Allow me to answer that. So actually, it's pretty cool. So I think Surendran has done a study on acquisition of sound pairs for children, not for second language learners. And he has found that high functional low pairs are learned first. So children will learn those first, and then now it obviously depends on learning, right? So to learn a sound pair, you have to produce them and perceive them accurately. And so it seems that in the acquisition process, more frequent or more contrastive pairs are being acquired earlier on. Perhaps because of, first of all, speakers, the input, people are acoustically enhancing these pairs. Let's say n and ñ is very, form lots of mineral pairs, I don't know whether it does or not. So people would phonetically enhance that in their everyday speech, the adult to the kid. And so they get very clear signals, so obviously they will represent them more clearly and you can perceive them more clearly. And over time, when they gather more lexical statistics, as infant doesn't know a lot of word initially. So the functional load, the internal functional load that they compute might be quite different from an adult. Whereas they gather more and more words, they know that, oh yeah, these two sound, mum is always using these two sound in a range of things. So I know that I better pay attention to these two sounds. Otherwise I will misheard it. I will get the terrible grapes as opposed to the fantastic mango. I don't know. And so both are terrible, both are pretty good. And so I think input from the speaker into the acoustic enhancement, and as they're growing up, the lexicon get bigger and bigger. They would have themselves reflect on, they will have a knowledge of functional load, and they will perhaps attune their perceptual processes to be able to pay attention to the cues that matters. And so going back to extending to the second language speakers, I would guess they would do the same thing. In many ways, they are like, they're not like young children, but in many ways that they are learning a language, they're capturing statistics, they are learning more words, and over time they know which word or which sounds are more important than others. So I would expect to see similar results with second language learners. And obviously then one factor you have to take into account is the fluency, right? The competency, the proficiency. So I'll be very interested in doing that. If you have the data for it, let me know.
I'll try to collect it.
Yeah.
Okay, we will try. Okay. Yeah, I mean, that's very neat what you're saying, because it really is in line with the experiments on the learning of constructions done by Goldberg and others, and the construction grammar approach, concerning constructions, the same thing. Like, if a certain instantiation of a construction is more frequent, then you learn this construction better. I mean, like, the frequency factor plays a lot. It really is easier to.
Oh yeah.
Yeah. So
I mean,
obviously,
we are
yeah. So
statistical.
it depends on the level.
Yeah, we're a statistical learner, no doubt. So we obviously would use statistics to help us learn. And I guess depending on your view of learning, some people also believe that on top of statistics, you still have something more innate that modulate learnability. So it's not everything statistics. So people do also artificial grammar experiments showing this. You can give two groups different kind of patterns, same amount of input, but one pattern typologically, let's say 80% of language have this pattern, the other pattern is only occurring in 5% of language across the world. And people with the same amount of input, they will learn the pattern that typologically more common, easier than the one that are less frequent, showing some kind of innateness bias. Depending on your count, you might believe how far statistics can capture language acquisition. Thank you.
Yeah, I have several questions. First, most of them are clarification questions, but some notes or comments. At the beginning, you showed us data on flat and liquid order and other.
Oh yeah. True.
And also on b and b.